thanks for the invitation. So I want to talk about two-point correlation functions of local observables in the end quantum circuits, and this is joint work with Takato Yoshimura, who's in the audience and speaking tomorrow, but about a different topic, and Sam Garrett. And it builds on work that I did previously with Sam Garrett, and then further back with Amos Chan and Andrea De Luca. So just to explain what I'm aiming at, let me start with some obvious definitions. So I have in mind some local observable, which I'm calling A alpha to label the observable, and a thermal average, and then I'm just thinking of the autocorrelation function of that observable. And although I've written evolution for a time-independent Hamiltonian, actually I'll be thinking about periodically time-dependent functions, and so you should think of time-ordered integral here. And because I'm thinking about flock A systems, this thermal average will always be an infinite temperature average. So obviously, this kind of quantity we're familiar with in many circumstances. So on the condensed matter side, if you think of excitations, for instance, in an ordered magnet, then you might see those by looking at an autocorrelation function, or if you have some diffusing density in a fluid, you'd see the presence of that in power law tails. So really the question that I want to talk about today is what happens in systems where you don't have quasi-particles, and what's more, there are no conservation laws. So you might imagine that in those circumstances there would be nothing very much to say, and so the point of this talk really is to tell you that there is something at what we call intermediate times, and what that means is a timescale that actually grows with the size of the support of the operator. So this intermediate time regime, where there's something unexpected happening, can be large if you think about operators with a large support. So the outline of what I want to say is here. I thought, since we haven't had anything yet on random quantum circuits, and since it's a fairly broad audience, I should start off by saying a little bit about what I mean here, and also particularly about the distinctions that are important for the perspective I'm taking. And then one of my themes is going to be that there's a link between spectral statistics and the autocorrelation functions that I'm interested in, and to talk about why that link is interesting, I want to talk about a feature of the spectral statistics in spatially extended many-body quantum systems, which is at least sometimes called the Thales time. And so the point of this section is really to explain how this feature in spectral statistics is related to autocorrelation functions. And then in the final section, I'll give a heuristic picture for the feature that we find, and then I'll talk in detail about the results. So partly from analytical calculations, but also numerical results. Okay, so I'm going to be talking about quantum circuits, and I'll be thinking about one-dimensional systems. So we have the one-dimensional coordinate horizontally and sites with a local Hilbert space dimension, which I'll call Q. And then the time evolution is represented pictorially, and at different time steps you couple nearby gates together, and in this example I'm coupling pairs of gates, pairs of sites with a two-site gate, which is unitary of dimension q squared by q squared. And although at any one time step or part of a time step we only couple pairs of gates, as time goes by coupling different pairs, the whole system is coupled together. And one reason why these systems have been studied a lot, of course, is that if you take these gates to be random, and in the simplest case, you take each gate in this picture to be independently random, then you can calculate analytically and without too much effort a lot of the things that it's interesting to know. And then the point to emphasize about this system is that if you write down a time-dependent Hamiltonian that gives you this kind of evolution, well, if you write down a Hamiltonian that gives you this kind of evolution, then necessarily it's time-dependent, and because it's time-dependent, in the first instance, no conserved densities, not even energy. So the obvious things to think about are things to do with quantum information dynamics, and so these models have been used to do calculations on entanglement spreading and on operator growth. So you can ask what other things are that it would be interesting to think about in the dynamics if you go beyond these very simplest versions of random unitary circuits. And I think there are two directions that you could go in. So one is to say what happens, to ask what happens if we put back a conserved density. So it's possible to design circuits which are still random from one time step to another, but which have a U1 symmetry. And so you have conserved density without having time translation symmetry, and you can look at the effect of that conserved density on operator growth. But another thing that you can do is reintroduce time translation symmetry, but to keep some of the simplicity of quantum circuits, you do that by not by going to time-independent Hamiltonian, but going to, in Hamiltonian language, periodically time-dependent Hamiltonian, that's to say going to Floquet circuits. So then we have time translation symmetry, but no conserved density. And in contrast to a time-independent Hamiltonian, of course, this time translation symmetry is discrete. So in contrast to the simplest version of a random unitary circuit, where the time evolution at each step was uncorrelated with previous steps, we now have a fixed evolution operator, the Floquet operator, and so we can look at its eigenvalues and look at spectral correlations, and this was what we did with Amos Chan a few years back. So just to emphasize the distinctions I'm making, in the simplest version of a random unitary circuit, we have gates independent at each time step, which is represented here by using different colors, and then it's possible to do exact calculations for general Hilbert space dimension. Whereas if we go to a Floquet system, then the gate that acts between a given pair of spins is the same each time it acts, and so periodically repeating time evolution. And then calculation is more difficult because for interesting quantities you have many copies of these gates, but you can do exact calculations when the local Hilbert space dimension is large.
When you say exact calculations, what do you have in mind? Like two-point function?
Well, so for instance, you can calculate the spectral form factor, or you can calculate autocorrelation functions of observables, as I'll be saying.
Like higher point correlation functions, can you do it for?
Well, we looked, I won't talk about it now, but in the same work with Takata, we looked at OTOX. So I said I want to make a connection between correlation functions of observables and spectra. So again, as background, let me talk about characterizing spectra. So I have here a Floquet operator, and the eigenvalues after one time step I'm writing as e to the theta n. We then to label the eigenvalues, and then after some integer number of time steps, the evolution operator obviously has eigenvalues raised to that power. And then the spectral form factor basically tells you about correlations between Fourier components of the eigenvalue density around the circle with the time argument labeling the Fourier component. And the simplest model for this is if you think about what happens when you represent the Floquet operator just by a full random unitary, that's say an n by n matrix with the Haar distribution. And then you find that the spectral form factor, apart from a peak at time 0, which is very large, it has a ramp and a plateau, and the switch between the two is set by the size of the Hilbert space dimension. So then the point is that when you go to Floquet quantum circuits, this expectation from random matrix theory of a ramp and a plateau is accurate at late times, corresponding, of course, to small energy separations, but you get something different at early times, and the dividing time between the two types of behavior, by analogy with ideas in single particle models of disordered conductors, is sometimes called the Thales time, although the term Thales time has been used for some other quantities which are probably distinct.
Question?
Yeah.
The form of this bump you think is universal for any local system without conservation laws? Do you know the form of this bump?
Yes. Yes, I think when yeah, for a lattice system, I think.
There's some functional form.
Yeah.
Which, okay.
Well, I mean, the functional form is derived for these circuits, but I think the features you would expect to be present in other systems as well.
It's derived at large Q, but
It's derived at large Q, but
the shape is universal, or I guess the fact that there's a bump is universal, but the shape.
Yeah, I think it probably should be. We can discuss how firm the basis is for expecting that, but the general picture which you have at large Q, I think we also have evidence for from numerics at finite Q. Okay, so there's a question then, what sets this timescale? And you can try and answer that by relating the spectral form factor to other quantities. And so far as I can see, the best way of thinking about it is probably to relate the spectral form factor to autocorrelation functions of observables. And there's a relation which I guess is probably familiar to a lot of people in different guises, which basically says with an appropriate normalization, a sum over all operators of the autocorrelation function gives you simply the spectral form factor. And one way of seeing that this should be true is easiest to explain diagrammatically, and it's basically the resolution of the identity in the vector space of operators. So the idea is that these operators here form a complete set acting on a Hilbert space dimension n, and if you form this sum, then viewing it as the resolution of the identity, you can represent that as closing off these two lines. And when you combine that with an expression for the autocorrelation function, which involves the operator, the time involution through some time t, the operator again, and then the inverse time involution, taking this sum gives you exactly the spectrum form factor.
This includes like very big operators.
It includes very big operators. And the ramp, okay, and then, so the implication of this is, well, firstly, the ramp that you would have in random matrix theory, that comes from very long operators, and then the deviations from the ramp over n times come from shorter operators, and so the many-body Thouless time should be the longest relevant timescale in operator dynamics, and that's partly why we were interested in this problem. So if you ask yourself what you would expect and just have something concrete to think about, we could think about a quantum spin chain, trotterized, that we have a flock A problem, and it'll become important that I'm thinking about ensembles of systems, so we could have on-site random fields, but these should be small enough that we're in an ergodic phase rather than an MBL phase. And so your first guess might be for some autocorrelation function that it would show irregular oscillations that would be specific to the particular realization of the disorder. But if you then did an ensemble average over different disorder realizations, you'd simply have smooth decay. And schematically, the actual average behavior that we get is more like this. And depending on details of the model, a lot of models that it's natural to pick actually have a zero at time step 1, and then you see a revival at later times. But more generically, you just have a tail, and it's the duration of this tail that grows with the size of the operator support. So to give an idea why that kind of behavior comes about, I've got a sort of toy problem which gives you part of it, but not all of it. But I hope it was worth thinking about. So suppose we have something like the quantum spin chain that I was talking about, and we're thinking about an operator with some finite support, which I've drawn here. Then, as a first step, you could think about autocorrelation functions simply cutting the support of the operator out of the system and treating that as an isolated system in itself. And then to make things simpler still, you could think about the time evolution within that small section of the system as being represented by some random unitary. And in that case, you find, again, the sort of ramp and plateau behavior that I talked about for a large random matrix. And if you normalize the operators so that the correlation function at time 0 is unity, then in this quantity, the ramp at late times is of size 1 over n, and it sets in on a time scale n. And then here is the Hilbert space dimension for this subsystem. And the calculation that gets you to that result is simply to expand in the eigenvectors of the unitary, and the autocorrelation function looks like this, and the average of the unitary is soon reduced to the spectral form factor with this normalization in front, which is consistent with the plateau boundary. And then the final stage of this heuristic argument is to say, well, what happens if we put back in coupling to the path, and if that somehow acts coupling to the rest of the system, and if that coupling acts as if the rest of the system were a path, then at later times you'd expect some sort of decay. So that was an argument which gives you some idea, I hope, for why there might be some interesting behavior at intermediate times. But now I'm going to talk about concrete examples. So if we're designing Floquet quantum circuits, then the choices that we can make are firstly the local Hilbert space dimension, and secondly the architecture for the circuit. And
ask a question. So I guess I'm a bit confused about what sets the separation timescales between the first drop and the later drop from coupling to the back. It seems like they're both order 1 timescales in general.
So this first drop, it's something that happens naturally in the ensembles you might first think of constructing, which are ones where the ensemble has invariance under on-site unitary rotations. So although I'm drawing continuous lines in these graphs, we're talking about a Floquet system, so T is integer. So
that's really the first, the time equals 1.
This drop is at time equals 1.
Right, it's a property of the ensemble average, whereas if you looked at a typical, if you looked at sort of the square average or something, it might not be as clear.
Well, probably wouldn't be there. Okay, so to specify particular models, you need to choose a local Hilbert space dimension and some architecture for the circuit. And I'll talk about numerical results from a brickwork model of the kind that I was showing before. And here the gates will describe a Trocherized version of a spinor-half Heisenberg model, but with random fields applying to each side, so as to give Haar rotations of the spins in between the actions of the coupling terms. And then I'll also talk about analytical results, and for that we need large Q. And at large Q, to stop the system being so strongly coupled that nothing interesting can happen, I mean that you somehow wipe out all interesting behavior in the first time step. To avoid that, then we need some adjustable coupling, and the system that we study is like this. So the flock A time step has 2 bits to it. The first bit, represented by these blue boxes, is on-site Haar rotations, and the second part is some coupling between sites with a strength that I'll call epsilon, which will come up in the results later on. And we choose this coupling unitary to be diagonal in a computational basis, so it just consists of phases, and these phases are independent random variables with mean 0 and variance, which sets the coupling strength epsilon. Okay, so the numerical results for the trotterized Heisenberg model look like this. So what I'm plotting is, in order to make the results look more impressive, not a single one of these correlation functions, but rather all of the correlation functions summed that have a given length to the support. So as you'll see, as I say more about the results, the interesting features in the correlation function are suppressed in amplitude when the size of the support is long, even though their duration increases with the size of the support. But that's counteracted when you sum over all the operators in support, because there are q to the 2l sub a operators supported on a length of LA. So the main point is this is a plot of the sum of these correlators with a given support against time in units of the flock A time step, of course, and the different colors correspond to longer and longer support. So the point is that something interesting is happening on these timescales, which are much longer than the flock A period, and what's more, the duration gets longer as you go through times. And the same thing is present analytically. So the form of the analytical result is shown here, and I'll talk in more detail about the different factors on the next slide. But the main point is that you have a term here, which is 1 plus something that's small at late times, but it's raised to a power of the length of the support of the operator. So the longer the operators, the more this factor becomes important. And the time scale for decay is a version of the Thalers time associated with operators of given support, and it grows logarithmically with the size of the support, and also would diverge if you turned off the coupling between sites.
Is it obvious to see how you recover the spectral form factor here if you sum over LA?
So, yeah, it is, but this is for operators which are not long enough to extend to the ends of the system or to wrap around the system.
I see, so the expression changes a bit. Once you
It changes a bit. I'll show you how it changes when I talk about the next slide. Okay, so the result that I had there has these different factors on the right-hand side, which I've colored, and let me try and explain how they come about. So the most important thing is the bit that's colored in red, and that's the dynamics that you would have for the observable if you separated the cluster from the rest of the system. And the fact that there's some kind of enhancement at large operator supports is something which I'll be able to say a bit more about bit about the calculations. And then there's some decay, which comes from coupling to the rest of the system, as in the heuristic example that I had. And then there's a factor which makes the whole effect small, Hilbert space dimension to the power of minus twice the system length. And this appears because a given operator evolves very rapidly into other operators with the same support. But in this model with weak coupling between different sites, the spreading onto other sites happens more slowly. And if we had an operator which extended, as you were asking, to the end of the system, then what we need would be this blue factor when we get back to the spectral, to the length and the spectral compound. So one thing that you might worry about is that both of those results were after averaging over an ensemble of systems, and so you might feel, well, if you look at some quantity with less dramatic averaging in it, maybe it's pretty hard to see these effects. And the point of this slide is to say that that's not really so. On the left, we have the autocorrelation function with a width to the lines, which is the standard deviation divided by root 10. In other words, if you average over 10 systems, you would be able to see results like this, and clearly some feature in the autocorrelation functions is present. And then on the right, we've got results from a single realization, but we're now averaging over all operators with a given support, and the width of the lines is the standard deviation over the ensemble. And again, you can see that in individual systems, if you average over all operators with a given support, then these features in correlation functions are pretty visible. And then the final thing I want to say about the results is what happens if you look at other models, and the models that I've shown results for so far have a special feature, which is that the ensemble of systems is invariant if you do on-site unitary rotations. And that actually guarantees that the autocorrelation function vanishes at time 1, which means that the effects that I've been talking about show up as a secondary peak. So if you're designing simple models, it's natural to have this invariance, but of course if you take some particular Hamiltonian or ensemble of Hamiltonians that you haven't designed for simplicity, then it won't be there. And to see whether interesting things are happening, one thing we can do then is to compare behavior in the Floquet system with behavior in an equivalent system, but where we take a different realization at each successive time step. And what you find is that in the Floquet systems, again, we have features extending to quite late times, whereas if we take a different evolution operator at each time step, then the correlation functions decay rather rapidly. So then I wanted to finish by trying to give an outline of calculations. And let me talk to begin with about how things would go if you're calculating the spectral form factor. For these Floquet systems, that's the trace of power to some k operator to some integer power, and so you can expand it as a sum over products of matrix elements, and you can think of this as a sum over paths in Fock space, and we can draw these paths in this kind of way, where we label the different sites with the corresponding states. So if we think not of the trace of one power of the evolution operator, but rather the product of two of these traces, then we've got two sums over paths, and in general, a term from one sum will have a phase that's nothing to do with the phase of a term from the other sum. But if the path in the second sum is related to the path in the first term by some global time translation, then the terms are just the same, and you get constructive interference. So pictorially, we can represent one possible pairing in the way that I've shown here, but we could also translate the sites that we form the pairing with in one of t minus 1 possible ways. So if you sum over all possible pairings, then you recover the ramp in the spectral form factor. And so that argument holds for a single height symmetry, but when we go to a many-body system, then you can have space domains with different pairings between the different time-translated paths, and you have an equivalence to a t-space model where you have t possible pairings in one domain and some statistical cost for the domain walls between different types of pairing. And when we apply these ideas not to the spectral form factor, but rather to the autocorrelation function, then the kind of calculation that we need to do is represented here. So, firstly, we've got the definition of the autocorrelation function as a trace with the operator and the evolution operator and the observable again, and then the inverse evolution operator. So the blue and green parts of the cylinder are representing the evolution operator and its inverse. And then if we have an observable acting on some support, which I've represented in brown, we've got some picture like that. So the pairings, the details of a picture like this at individual sites are represented down here. And when we start averaging, then at sites away from the observable, we have a single leading contribution, but at the sites where the observable acts, if it's traceless, then we don't have a contribution from a term like this, but we have some number of leading terms, which grows with the number of time steps. So when you put these ideas together, we get a contribution to the autocorrelation function, which grows with time from this growing number of pairings, but we also get suppression from domain walls between this type of arrangement and the arrangement that's preferred outside the support of the operator. And it's the competition between those two that give the results that I described. So to summarize, what I'm saying is that autocorrelation functions and observables have structure even in chaotic systems with no conserved densities. And these features transformation functions have a link to the Fowler's energy that's important for spectral correlations. And I think in principle this would carry over if you had time-independent Hamiltonians, if you considered observables that you constructed to be decoupled from the conserved densities. Okay, so thank you.
So if I understood your picture initially, you said, okay, this growth should be like on the, it should take as much time as like the size of the operator, like something like this. Like, I think in the completely random unitary, you have a picture that's like, it has size n and then it takes n steps until it like.
Well, yeah, you have an initial growth until the coupling to the rest of the system cuts it off. And from that heuristic picture, I think it's not clear when the coupling to the rest of the system will cut off that growth.
But so in the pictures that you, like in the simulations to the end, it was really rapidly, like the growth was 1 or 2 time steps or so. Do you have situations for like observables that are like very big where you have like a longer like growth before the decay?
Well, probably the best thing is to go back to the analytical results. So the one parameter that controls things is this epsilon, the strength of the coupling between sites. So if you make epsilon very small, then you have then the maximum is at later times. So you can engineer that.
So how does spatial dimensionality show up here? Because I guess you have more big operators if your spatial, I guess there's both the size and the sort of, and you know, the contiguous.
I think the effect of being in higher dimensions, I mean this e to the minus 2 epsilon t, the 2 is just the 2 ends of the operator. So if you have some boundary to the operator, that 2 would become the size of the boundary.
And would that explain, I guess, this old result of yours that that the Thales time is order 1 in higher dimensions and order log L in 1 dimension? Is it because you think guys?
Yeah, actually, I think I no longer stand by that claim. So the basis for that claim was that in higher dimensions, the Potts model has a transition, but actually to get the full random matrix behavior, I think you need to do more. You need to eliminate all excitation. So I think probably it's still logarithmic in higher dimensions.
What's happening in the pairing picture when the coupling to the external path is becoming important?
I'm not sure if I
because I'm assuming that within the operator support region, right, you have order t number of distinct pairings.
Yes.
And in the outside world, there's just the one privileged pairing. But then for some reason, when time becomes large enough, somehow the something about the t-fold degeneracy of the Goldstone mode, it ends up somehow being washed out. And I'm just trying to understand why that's the case.
is your question whether at late times this pairing somehow gets imposed on that side?
Yes.
Yeah, we do have a picture for that. Yeah, I'm not sure I can reproduce it accurately on my feet. I'll try and remember it and tell you what it is.
So if not, let's thank John again.